Hey guys, this is Academia on Demand and I'm Josh Myers and I am bringing you another video involving the study of the theory of covalent bonding. So, in the last video we were introduced to the ideas of the Vesper theory, which was essentially laid out the premises for what we will later come to have known as the Lewis theory, which is the drawing of molecular structures. And that is the central focus eventually of what we will come to understand about covalent bonding and about molecules and their different, what we would like to call idiosyncrasies, all their different formations and structures, and that is what we will be talking about in this video. But first, I made many annotations in the last video regarding different specifics, different little gaps of understanding that I may have left out in the last video. So in this video, we will be going over those a little bit more closely before we go into the main theory stuff that I want to do. Okay, so the first thing that I wanted to talk to you guys about is the idea of ionic, this idea of ionic versus covalent character. And this character word, it's a very interesting choice of words, but it seems to make sense once I explain it to you, hopefully. Okay, so the ionic versus covalent character. So as we know, ionic and covalent bonding from a perspective of where the electrons are, whether they in an ionic bond would be closer to one atom than the other, or therefore accepted by one atom or the other, or shared by both atoms. These two concepts of ionic and covalent bonding are inverses, or what we would like to call, what should I call them? I should call them opposing concepts. So they are opposing concepts. Opposing concepts. And as we learned in the last video, the instances when ionic bonding is used versus covalent bonding depends on the change, the delta En, the change in electronegativity from one atom to the next. So the difference in electronegativity depends on delta En, which is the difference in electronegativity in the bond of one atom relative to the other. Okay, but so how does this word character fit in? How does this word character fit in? Well, what this word character says is that because they are opposing concepts, because they are what we would almost like to say dual concepts, they exist on a continuum. So they exist on a continuum, which means that most of the time, when molecular bonding is occurring, there's a little bit of both. There's a little bit of both, which means that on one extreme, let's just draw the continuum, and then I will tell you exactly what everything means here. So covalent, so if a bond was completely covalent, 100% covalent, it would be sharing the electrons. It would have the electrons in the middle of the molecular orbital, and this is actually achieved. So as we know, nitrogen from last video, and let's not do nitrogen, let's do one of the halogens, let's do chlorine. So as we know in last video, when we talked about diatomic covalently bonded molecules, they exist as two atoms bonded to each other, even though they are essentially representing the element of chlorine here. So chlorine only exists in nature as bonded to itself as Cl2, the molecule Cl2. And in this molecule, because as we discussed in the last video, one chlorine has a certain pull on the electrons because of its electronegativity value, and the other chlorine has the exact same pull on the electrons in this molecular orbital. Well, the resulting fact is the idea that the electrons stay almost in a neutral state, where they're not pulled towards one or the other because the pull is the same. So therefore, they would be in this ideal world where they are shared, where the electrons are shared. So why am I calling this a continuum when there actually is a situation where a bond can be 100% covalent, where it can be completely covalent? Well, because in the middle there exists many other bonds that kind of consist of a combination of these two ideas. So, for example, in the last video we talked about FeCl3, and it had the FeCl bond has a delta En, a change in electronegativity, a difference in electronegativity of 1.4. And this, I deemed it to be more ionic than covalent in the sense that the iron as a metal achieves great energetic stability when it simply gives away 3 electrons. When it simply gives away 3 electrons, it has a half-filled 3d orbital, and it has an empty 4s orbital. So it achieves great energetic stability when it gives away its electrons, which represents the idea of ionic bonding. Whereas chlorine would love to gain these electrons. In fact, 3 chlorines would like to accept these 3 electrons in order to gain outer energy levels. And in this way, it makes sense that therefore, if Fe3+ was created, then therefore the chlorines, which have a negative charge, would attract each other. They would attract. And so this logic seems to make sense, and at that point in the video when I was performing this example, it also seemed to make sense with allowing you guys to understand some ideas before others. But this idea of completely giving these electrons away as reflected by the electronegativity value is not totally accurate. There is some sense of covalent bonding rather than just complete ionic bonding. And so if we were to draw out FeCl just for a second, this is probably not so accurate, because in reality FeCl is from a majority perspective ionic. It is from a majority perspective ionic, just because, as I discussed earlier, the idea of the energy levels, the energy ratios almost, it just seems to make sense that it would give electrons away. But if we look at FeCl3 as this structure in a sort of covalent structure, and we were looking at the bonds, we were looking at these, what we would call these areas of electron density, then what we would see is that these bonded pairs of electrons in the molecular orbital are much closer to the chlorine. They are much closer to the chlorine. Much closer to Cl, and that is very poorly written, but I'm hoping you'll still be able to tell what I'm saying. So it is much closer much closer to Cl than to Fe. And what this creates is an idea of, because the electrons favor from a space perspective the Cl atom over the Fe atom, this sort of idea of charge is created, because as the negative charges, as the electrons which represent negative charges move away from iron towards chlorine, chlorine becomes more negative, whereas iron becomes more positive. Until eventually, obviously, in the ideal scenario, in which here, if it was perfect ionic bonding, the electrons would be completely transferred. And the idea of the molecular orbital wouldn't exist, and it would just be an attraction of ions. Attraction of ions. And so this idea of this continuum, because as we know, 1.4, you compare it to different electronegativity differences of, say, the compound LiF. LiF, which has a change in electronegativity, a difference in of electronegativity of 3.0 the FeCl3 molecule is relatively less ionic than the molecule LiF. And so what we're seeing here is that as delta En increases, the molecule takes on a greater ionic character than a covalent character. And so just before I stop rambling here and I go on to the next topic that I wanted to talk about, one of the biggest ideas here is the idea that although there are many different electronegativities, so 1.4, 3.0, what many textbooks, what many academia sources like to count as the cutoff between being ionic and being covalent is delta En of 1.7. So anything above 1.7, if we wanted to pigeonhole the idea, then we would say it is an ionic bond. So in this way, maybe we could say that the majority of it is an ionic bond, rather than saying that it is all an ionic bond, because as we know, there's a big continuum between, say, LiF and Cl2. So now that we have that idea down, and that idea will come in handy a little bit later in this video and then in many future videos when we talk about things such as intermolecular force, we will go on to draw some more molecules and practice our skills a little bit more with drawing what we call these Lewis structures. These Lewis structures. Okay. So as we saw in the last video, when we drew out our CO2 atom, it had a linear geometry once we determined where the electrons were placed in the outer energy orbitals. Where the electrons were placed in the outer energy orbitals. And that took the idea of where we were trying to put the number of valence electrons. So let's just go back for a second. If we said CO2, because we know that oxygen has 6 valence electrons and there are 2 of them, that means there are 12 valence electrons. And then finally there are 4 valence electrons in carbon. So therefore we have 16 electrons to work with when trying to complete all of the outer energy levels through the idea of sharing. And even though we know, as we just talked about, there is a certain degree of ionic bonding in any sort of structure that has some electronegativity difference, for the purposes of this video and for drawing these Lewis structures, for practicing this skill, we are going to assume that it is complete sharing and that these electrons need to be shared across all 3 atoms in this molecule in order to give them outer electron levels that have outer energy levels that have 8 electrons and thus achieve energetic stability. So we know that it has 16 electrons, and as we reasoned in the last video, because we know that carbon is the single atom in the molecule, it is going to be the center one. And then it makes sense because we know that it has to be bonded to 2 oxygens, that if we want it to have 8 electrons, then it has to have 4 bonds, or what we would say 4 molecular orbitals. Though this is not technically correct, they are not all molecular orbitals, as we will see in the hybridization video. Right now I want you to pretend they are. Okay, so the 4 bonds in this represents 8 electrons and a full outer carbon energy level. So then they are bonded to oxygens. And then these oxygens bond to the carbons, they each have 4 electrons. And now there are 8 electrons remaining after the bonds, so therefore each oxygen can have 4. So 2 what we would call non-bonding pairs of electrons. Non-bonding pairs of electrons, and we will talk a lot more about them today, but the point of this is that because of the way when we look at these areas of electron density relative to each other, they want to spread out maximally, because we know that one of the, what we would say, premises of the Vesper theory is repulsion, is electron repulsion. In fact, if we want to say repulsion of the areas of electron density, as we will see in this video, lone pairs are very good at repelling other not lone pairs. So now that we can move on to this, hold on, before we can move on to this, I am just getting ahead of myself here. We have to say that this is 180 degrees because, as we know, there are two bonds, and so if we want them to be a maximum angle apart to achieve this favorable geometry in which they are as far apart as possible, they must be 180 degrees apart, and the molecule is called a linear molecule, linear covalent molecule. Let's just write linear here though. Okay, linear molecule. Okay, so now this is 15 minutes, and I always do this to myself. But let's go through some examples. So the first example that I would like to look at with you guys is the example of the molecule boron trifluoride. So BF3. Okay, so as we know, first thing we want to do is find the number of valence electrons in order to draw this structure. So we know boron has 3 electrons, and we know fluorine has 7 electrons in its outermost energy level, so 7 times 3, and altogether this is 21, that's 3. We have 24 electrons to make this structure with, because as we know, another premises of the Vesper theory is that it only involves the valence energy levels of the atoms. Okay, so 24 electrons, and so we know that boron is the central atom. It is the one single atom element of the molecule, whereas there are 3 fluorines, there's only 1 boron. So let's put boron in the middle. Okay, so how are we going to make boron have an outer energy level of 8 in order to achieve its energetic stability? Let's move this down. How are we going to do this? Well, before we go on a tangent and try to maybe make a double bond with one of the fluorines, because as we know, there are only 3 fluorines and we need 4 bonds in order to make it energetically stable. Before we do that, let's make a single bond of each one. Okay, so if there's a fluorine, and then let's draw the lone pairs that complete the fluorine's outer energy levels, because sometimes it is easier to see how the atoms around the central atom achieve energetic stability before we say how the central atom will achieve energetic stability. Okay, so F. And so I've drawn 3 bonds with boron and fluorine, and then 3 electron lone pairs around each of the fluorine atoms. So let's count the number of electrons here before we decide how this is going to work. So there are 6 electrons in the lone pairs, and then another 6. So that is 18. And then finally, 2 electrons in each bond. That is 2, 4, 6. 6 times 8, 6 plus 18. 6 plus 18 equals 24. And so we would seem that we would have a really big problem here, because as we know, we only have 24 electrons to work with. But if the number of electrons is used up, how do we make boron stable? How do we make it have 8 electrons? How do we make it have 8 electrons? How 8 electrons? And I'm writing here like I'm skipping words, like I'm trying just to get down the ideas rather than the specifics. So how do we get 8 electrons? Well, the answer is that, well, we don't. And this seems like, Josh, why would you ever give us this rule if it's just going to be broken? Well, children, unfortunately, sometimes there are exceptions. In fact, there are almost always exceptions to rules in science. And this is just one example, and we're going to have to just deal with it. It's going to be there, it's going to be looking us in the eye with this ferocious look on its face, and we're just going to have to stare it down and say, "You do not scare me." So this is exactly how you would draw the BF3 atom as its Lewis structure, assuming that it is a completely covalent It has complete covalent character, as we said at the beginning of the video. And so if this is the Lewis structure, what are the bonds between these fluorines? What are the bonds here? Okay, and so as we know, if you take a circle, because these fluorine atoms, they are actually, if you were to take the molecule and look at it from a certain angle, they would actually all lie on the same plane. So therefore you can draw their angles in terms of a circle. So if you split a circle into three, let's see if I can do this. Oh, okay, let's try. And let's hold on for a second. Maybe let's try this. That's not too bad. Okay, so if you split a circle into three, we know that 360 degrees is therefore divided by 3. And this gives you a value of 120 degrees. And that is exactly what the angle between the bonds here is. Between these bonded pairs of electrons in the molecular orbital, the bond is 120 degrees. So now that we know the bond is 120 degrees, all of these are equally spaced apart. You cannot do anything else to these atoms to get them to be more spaced apart from one another. So we are done, 120 degrees, and this molecule is called a trigonal planar. Trigonal planar. We are not planning, we are planar. Okay. Planar. Okay, so let's do one more example and then I'm going to wrap it up. I'm going to save this for a final video, on Lewis and Vesper structures, and there will be no more clarifying in the beginning. We're just going to practice this skill as it is. Okay, so let's erase this guy at the top, and we will look at one of the most common molecular geometries. We're talking about trigonal planar as one of the molecular geometries. We're going to look at one of the most popular molecular geometries of any molecule, and this is to a big credit to carbon. Carbon absolutely loves this type of molecular geometry. So let's focus on carbon. Let's draw the molecular Lewis structure of CH4, and this is methane. And when we do organic chemistry, we will discuss methane and other organic compounds, what we call the alkanes, in large detail. Okay. So CH4, and so first thing, as we know, we want to find the number of valence electrons that we have to work with to make this molecule energetically stable, each of the atoms in it having 8 electrons. As we know, most of the time, the rule that was broken here holds. So carbon has 4 electrons in its valence energy level, and then each hydrogen has 1 electron in its valence energy level. And since this is times 4, there's another 4 electrons, because there are 4 hydrogens. This is equal to 8 electrons. So we have 8 electrons to work with. And so this seems simple enough, because as we know, hydrogen gains energetic stability when it only has 2 electrons in its outer energy level. Because as we know, the first energy level consists of only 1 s orbital. Okay. So if we draw the central carbon atom, because it is the single atom, the central carbon, and then we bond it to an H, an H, an H, and an H. Let's look at this. Are we done? Because I see 8 electrons here. So 8 electrons are bonded to the carbon because they are shared in the orbital, in the covalently bonded molecular orbital. And then the hydrogens, they only have 1 bond, but it has 2 electrons. And as we know, as we just said, hydrogen only needs 2 electrons to achieve energetic stability. So we are done. We do not need to draw any lone pairs. There are no electrons left anyways. We are done. So what is this? What are these bond angles? And this is where 3D space starts to play tricks on us, because we can't now simply say 360 divided by 4. That would be wrong. That would be not science. What we have to do is, what scientists have determined is that 3D space works in a different way. That we can't say 360 divided by 4 is equal to 90 degrees. That is not the maximally repelled angle between the CH bonds. Because of 3D space, they can actually spread out more because they don't have to exist on the same plane as they do in the trigonoplanar. So remember, as I said before, it is all of the bonds are on the same plane. Can exist on one single plane. But here they can't have this. That they actually can spread apart and take advantage of 3D space where they will not exist, all of them, on one particular plane. And so I'm just going to give you the bond angle. The bond angle for any structure like this is 109.5 degrees approximately. Obviously this is not exact. There are slight decimals. I think it's 109.47 something. I'm not quite sure. But if we just say 109.5, I will forgive you for being not specific because we could go on and list digits all day. So 109.5 degrees, and any molecule that has 4 things bonded to it, so 4 areas of electron density that represent bonded pairs of electrons around a central atom is called a tetrahedral. A tetrahedral. And we can remember this because tetra is symbolic. I think it might even be Latin for the idea of 4. For 4. So 4. And this means there are 4 groups around the central atom. Okay, so do I have time for one more? Okay, no, I don't want to risk it. But so next video we will talk a lot more about how the extra repulsion that I've been talking about from lone pairs affects the molecular geometry of Lewis structures. So examples such as ammonia, which is NH3. NH3, and the lone pair of electrons on the nitrogen atom repel these hydrogens very strongly, as we will talk about in the next video. See you guys.